Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be talking about all of the various types of IMFs you can find in nature. So these intermolecular forces are often split into many different categories, but they all fundamentally are based on what sort of forces are in play. So what is going to be the nature of those molecular charges on each atom or molecule? So we're going to go ahead and walk through these forces from strongest to weakest. So the strongest type of IMF is going to be the ionic forces. So this is where we've got two ions, a cation and an anion. So positive attracts negative, the two molecules are pulled together. So one of the things about these forces is that they do tend to be quite strong and quite resilient, but they are also kind of limited, as individual negative charges do not like being next to each other. And as a result, they tend to form very rigid solids where you have alternating positive and negative charges. So in this case, they're very hard, but they can also be very brittle, because when you start breaking the solid, it all has to break at once to minimize the potential of like charges interacting. Also, due to their high strength, they aren't always regarded as intermolecular forces. They're often sometimes characterized as actual molecular forces, as these ionic charges interact so strongly, they're often called ionic bonds. And so depending on the resource you use, you'll either find ionic forces listed as bonds or IMFs. So do watch out for that when you're when you're using other resources. One of the other important things to realize about these ionic forces is that only a single part of the molecule needs to be charged. You can have something like sodium acetate, where we have a negative charge split up over these two oxygen atoms and a positive charge on that lone sodium. But it doesn't matter that this part of acetate is uncharged. You still have ionic forces holding this whole system together. And as a result, it will form a crystal salt. And we'll talk about the forms of these salts much later. Now, we can't always guarantee that both of our atoms will have a full charge. One of the things that often happens is we're going to have an ion having to interact with things that aren't ions. So the strongest interaction this ion can have, besides another ion, is called an ion-dipole interaction. So these tend to occur when you have an ion interacting with a dipole or a polar molecule. So this would be something like water that has a positive end and a negative end all the time. So that positive cation will be attracted to the negative charge of the molecule. And if you had an anion, it would be attracted to the positive end. So these two hydrogens. And as a result, you have something that is actually fairly strong. This positive charge sees a negative charge. That partial negative charge on the oxygen sees a full positive charge. So it's like, dang, I'm going there. And this ends up making quite sort of positive interactions. Additionally, you'll tend to see this IMF grow in strength as you have a higher charge on your ion. So when we go from sodium to magnesium, the interaction would be strengthened. You'll see the same thing with anions. You'd expect oxides or O2 minus to be much more stronger than a simple chloride. Similarly, the stronger the dipole, so the more polar the molecule is, you are also going to see a much more strong interaction in between our dipole and the ion. However, one of the problems with these ion-dipole interactions is that our polar molecule has to be mobile enough that it can make sure that it can arrange all of those negative charges to interact with positive and the negatives with positives. So again, this does take a certain degree of flexibility. However, one of the reasons why water is so famous is it's very easy for water to rearrange and guarantee high ratios of positive-negative interactions without introducing much positive interactions. However, not all polar molecules have quite the same level of flexibility, and it's something to keep your eye out for. Now, if I have a polar molecule and it can't find a full charged ion, it essentially has to settle with finding another polar molecule. So this is our next strongest type of IMF. where we've got two molecules, both with partial positive and negative charges. And then again, positive aligns with negative, negative with positive. And they tend to try and line up in ways that will maximize these positive-negative interactions. So this can either be a sort of side-on motif, as you see with iodine chloride, or it can be a head-on, one iodine with one chlorine, positive with negative. But we're also going to need to make sure you arrange it so that none of the positive charges are next to each other. So again, this does require some sort of flexibility when you're making a solid or a liquid. And in general, these IMFs are going to be stronger with the greater the dipole, because the more polar the molecule is, the greater the partial positive and negative charges present. So that means that every ion will see a greater charge and you'll have that greater interaction. You may start to see a very reoccurring motif. However, this can also occur in more complicated molecules like acetone, because acetone, while this carbon, these two carbon atoms aren't going to generate much charge, does have a partial positive on the carbon and a partial negative on the oxygen. And so you'll often see things like acetone make these net dipole sort of interactions in a chain to maximize these sort of interactions. One of the things that is worth noting is that you can get a little bit of extra bonus on these dipole-dipole interactions if you have a more polarizable molecule. So larger molecules, more flexible electrons, such as is present when you introduce a double bond. However, it is worth noting that polarizability is only a little add-on. In general, the strength of the dipole, so the polarity of the molecule, is going to be much more important than anything polarizability can add. Now, to emphasize this point, there is a very special set of molecules that is worth noting. And these are three special types of bonds that are so polar, they deserve their own category of IMFs. And this is the nitrogen-hydrogen, oxygen-hydrogen, and fluorine-hydrogen. All three of these bonds are incredibly polar, and they guarantee that our anionic part has open areas of negative charge in the form of these lone pairs that can interact with the positive charges of the hydrogens. And so if I have an interaction in between any molecule containing any one of these bonds, you generate what is called a hydrogen bond. So hydrogen bonds are essentially a way of talking about the fact that I can get a hydrogen atom to coordinate to be covalently bound to one of these atoms, nitrogen, oxygen, or fluorine, and have a intermolecular force to another one of these same atoms. This generates quite a bias of charge, and because of the flexible nature of these bonds and their great polarity, it's a good way to make sure we can guarantee those positive and negative charges can rapidly approach each other with a great deal of strength. And these are one of the most stable types of IMFs you can get. This side of an ion being involved, it doesn't get much better. So whenever you're looking at the polarity of a molecule, remember, hydrogen bonds always win. Look for these motifs and you'll know you've got a strong IMF. Now, one of the other really useful parts about these hydrogen bondings is because we have this mix of positive and negative charges, they tend to form very nice, stable networks. And they also tend to be very flexible, as it's really easy to substitute out one molecule for another. And as a result, you'll often find many liquids or solids will contain these types of hydrogen bonds. And it is important to remember that hydrogen bonding can also be present where only some of your bonds are NH, OH, or FH. So if we have something like DNA, DNA is made of nucleic acids, so it has a lot of carbon, oxygen, and some nitrogen and some hydrogen. Now, it turns out that your DNA is held together by a series of hydrogen bonds in between each strand of the DNA. So each strand of your DNA forms a separate molecule, but along the edge of these molecules, you have lots of either oxygen or nitrogen atoms and lots of hydrogens. They can line up positive with negative, negative with positive, in a very predictable arrangement. And this is what allows your base pairs in DNA to line up and hold together fairly tight. And this is strong enough that we rely on it as a way of containing information. So your body relies on hydrogen bonds to get things done. And they are going to be very ubiquitous when we talk about any sort of intermolecular behavior or interaction. Now, it is worth noting that these three types of dipoles and these three hydrogen bonds do form exceptionally stable networks. And you can see this with boiling points. And we'll talk about this later, but boiling points are a measure of the stability of a given molecule. And we find that in general, as we go up in larger molecules from water to hydrogen sulfide, to hydrogen selenide, to hydrogen telluride, and this occurs for all four groups, you tend to get much higher boiling points. And the reason why is as you go across, you become more polarizable. You can generate more of those partial positives and negatives. And this is a fairly consistent trend. However, take a look on this first group, because oxygen, fluorine, and nitrogen are so much more electronegative than everybody else. They kind of break the trend, and they are way higher boiling point liquids than you'd expect just from basic dipole interactions. So really emphasizing the stability of these hydrogen bonds. Note that carbon does not have that same degree of electronegativity. It doesn't have any available lone pairs, and so it's about right where you'd expect. It is really unstable. And as a result of this extra bonus stability, there is a reason we tend to find hydrogen bonds commonly throughout nature. Now, however, it is worth noting that oftentimes you can't rely on just having polar molecules around. Sometimes you're going to have non-polar molecules like oxygen, like nitrogen gas, just wandering around as well. And one of the things that can happen is you can actually get molecules like O2 and N2 to interact with other systems using what's called a dipole-induced dipole interaction. It is not nearly as strong as a dipole-dipole interaction. But what ends up happening is if I have something like water, which is very polar because of its hydrogen bonds, and I place it near oxygen, well, that partial negative charge on water can induce a partial positive charge on oxygen, just temporarily. What we're watching is those electrons swishing from side to side using that polarizability. And so the electrons will shift away from this oxygen, generating a negative charge over here, positive charge over here, which pulls the oxygen just a little bit closer, makes it a little bit more stable in water. And in general, this force is going to be dependent on how polar my polar molecule is and how polarizable my nonpolar molecule is. The easier it is to shift those electrons, the tighter it will be held. That said, it is worth noting that this is kind of a poor deal for the polar molecule. In general, if I was a polar molecule, if I was water, I will interact with oxygen, but I will not interact with it nearly as strongly as another water molecule. So in general, we'd expect water to prefer to hang out with water, but it can help stabilize interactions with non-polar molecules. It isn't great, but it does work. Now, if no polar molecules polarity is present at all, and all I'm dealing with is non-polar molecules, we have the leftover force, induced dipole, induced dipole. So the idea here is that I've got, say, two nonpolar atoms or molecules. Take helium for a simple example. They have really no interaction, but electrons move from side to side. And so one of the helium atoms can have a partial positive charge form on one end. Well, this can induce a temporary partial negative charge on the other end. So really what we're doing is watching water slosh back and forth inside of each of these atoms which causes those electrons to swish back and forth in the other atom, generating these temporary attractive forces. So we're temporarily generating these partial positive and partial negative charges. They come and go, and so they aren't going to be exceptionally strong. And it is worth noting that this is going to be the weakest of all of our intermolecular forces because IMFs are dominated by the presence of charge. There is no permanent charge here. There's only temporary charge, so it will be quite weak. However, you can strengthen it by making the molecule or atom more polarizable. So again, we're watching the strength of this IMF rated the same way we rate the polarizability. Xenon is more polarizable than krypton, than argon, than neon, than helium. This is one of the reasons why you can actually get liquid forms of these heavier noble gases a little easier than you can with helium, which doesn't form a liquid until about 4 degrees Kelvin because it has no IMFs to make. That said, while induced dipoles are fairly weak forces, their big advantages is that they are always present in everything. And because they're so ubiquitous, they also are more commonly known by another phrase, London dispersion forces. And the reason why is they can be very dispersed over an entire molecule. Because it turns out every molecule is polarizable to some extent or another. Not every molecule is polar, but every molecule can be induced to get some sort of polarizability. Now, you can take something like a big alkane chain. Most of your fats will act the same exact way. There is no net dipole on a carbon-hydrogen bond, but I can make the electrons shift away from one side and towards the other. Now, if I've got a nearby carbon chain, well, the negative charges will now be attracted to the positive charges, and this will bring the two molecules together. And this really helps lead to the greatest power of these London dispersion forces or dispersion forces, is because they're ubiquitous and everybody has them. What we can do is instead of having few strong attractions like in hydrogen bonds or ions, what you have is lots of little attractions. So lots of little positives and negatives forming, which can make quite a strong net sort of intermolecular force. So a good way that I like tending to look at this is that hydrogen bonds are more like the buttons holding your clothes together. London dispersion forces act like Velcro. Any individual patch of Velcro will not be nearly as strong as a button the same size. But the advantage of Velcro is you can have a whole lot more of it. And because the fact that these London dispersion forces will scale with size, the more molecule you have, the more forces are present. This is going to be the general reason why heavy molecules tend to form liquids and solids, because they have more of these London dispersion forces holding the molecules together. And it isn't actually have anything to do with the weight of the molecule. It's entirely based on the strength of its forces. Now, when you're looking at a system and you're trying to figure out what force am I dealing with, one of the big things you can do is try and walk through this tree and figure out what sort of groups are present in the molecule and what sort of forces it can involve. So when you look at a molecule, the first thing you want to do is figure out if there are ions involved. If there are ions involved, it will make some sort of ionic connection because these are incredibly powerful. So they will be the most important. Now, what you need to do is say, is it just ions? If it's just ions, you've got ionic bonding. If you have polar molecules like water or ethanol present, then you're going to have ion dipole forces present as well. Now, if you don't have any ions, and this is mostly the case, the big thing you're going to be looking for is, are there polar molecules? So you're looking for something where you have two atoms next to each other that are fairly removed on the periodic table. The special category of this is, do you have hydrogen next to nitrogen, oxygen, or fluorine? In this case, you have hydrogen bonding. If not, you're just going to have dipole-dipole. That's just fine, but not quite as strong. Now, if you can't find anything else, and honestly, even if you can, you will always have London dispersion forces available. So one of the big things I do like to emphasize is what we're looking for on this chart is just what's the strongest force present. Just because you have one of the strong forces present, doesn't mean you won't have other forces present as well. Remember, everybody gets London dispersion for free. If you're hydrogen bonding, you technically also have dipole-dipole. If you have ion-induced dipole, there's likely some form of ionic bonding and some form of dipole-dipole present. But always pay close attention to which one will be most important in any given situation. Now, one of the reasons why we've been talking about these in the order they have is we're always based on strength. And one of the things I like to emphasize is what's causing these forces. Again, it's going to be the size of the charge and how it's generated. Is it permanent and greater than 1? Is it permanent but less than 1? It isn't a full charge. Or is it impermanent? Is it only present some of the time? And again, as you note, the stronger the charge and the more permanent, the much stronger these forces will be. And in general, pound for pound, LDF is the weakest. Now we've gone ahead and given a general overview of IMFs. Next time, we're going to go ahead and do a quick jump talking about how we can apply these principles of intermolecular forces to more common scenarios. Until then, take care.